screen here, it should say like battery and stuff.
Yeah, it's
Yeah. Yeah, and if it stops working, just tap it a few times and it should work.
Okay.
Okay. Ja, ik
Start from the studio. Because we had the limit, so it's just going to be right. So we will just start from the schedule. Yes, yes, you find everything.
I would consider like if we were being on bigger yes.
Should we start? Should we start?
Yes, I think we can start.
Okay, so I think we can start. Just for your information, you can find all the material in the schedule in the slot for this tutorial. Once it will load, it does not load anymore. But if you go to the schedule and in the Skrub description, you will find at the bottom the tutorial and the link. And you will find the GitHub repo, which looks like this. And if you want to follow with us, there will be some exercises in the repo. You will have to clone the repo. It will be a bit big because it contains the data sets that we're going to use during the tutorial. And you will also find the website that contains all the material for a tutorial as well. And there are a few ways to work with the tutorial. The simplest way is probably to just use Pixie if you have it installed. And you just get it from the official website, and then you can run some of the commands here. Otherwise, we're also providing the requirements if you want to use a usual virtual environment with UV, and you can also have the environment to use for Conda. And another way you can play with this is with Jupyter Lite, which is this button here that will start the session in your browser, and you don't have to install anything. It will just prepare everything for you. And I will start with a short presentation so that people can kind of set up their environment using the readmes. And then we will be going through the first will be a very short notebook, and then it will be the rest of the tutorial. But yeah, I am Ricardo, Guillaume is here, he will be doing part of the tutorial, and I will be introducing Skrub for now. And this is just an introduction of the main concepts of the library. So the name of the library is called Skrub, with the tagline of machine learning with data frames. And first I will say I will be introducing what Skrub is, a few of the simple transformers that Skrub use, and then introduce some of the concepts of the data ops, which is a major feature of Skrub that is what we will be using during the actual tutorial. And then I will be moving on to the actual tutorial, which is about forecasting with the Skrub data ops. The idea behind Skrub is to boost your productivity whenever you have to do machine learning with data frames. So the idea is that There are a lot of preprocessing things that you have to do whenever you have to prepare a data frame so that you can use a machine learning, usually a scikit-learn pipeline with the data frame. Like you have to cast data, you need to extract features, you need to do a bunch of stuff. And the idea of Skrub is to save you time and effort by doing a lot of the usual transformations that you have to do for you. So, a pipeline that you would probably be working on if you have to do something with scikit-learn. You have to gather some data, you want to explore the data, you have to pre-process it, find the correct data types, remove the null values, also all that stuff. You need to do feature engineering, like you have categorical features, you have numbers, you have date times, how do you convert them all into numbers that can actually be digested by a machine learning model. Then you're going to build a scikit-learn pipeline, and hopefully you profit. So the first step, now we are assuming that you already have your data, is you want to explore the data with Skrub. And Skrub provides the table report, which is this very simple command. You import the table report, you run this on a data frame, pandas or polars. Anything that you're going to see here for Skrub is completely supported in both pandas and polars, and the tutorial will actually be using polars. Oops. And what you're going to see from a table report is something like this. Let me just zoom in a bit if I can. I will be going into more detail also in the tutorial, but the idea is getting HTML formatted, more richer display of a data frame that gives you a lot of information about what's inside the data frame than what you would get with pandas or polars. So you can see all the columns that you're working with. You can see a bunch of statistics about each column, the data type, the number of unique values, null values. You can actually see all the distributions of categorical values to see what is the distribution of stuff that you're going to deal with in your data. So you can find that some of the classes are more frequent, whether a particular feature is very imbalanced. And this is all done for you, this is all pre-computed for you whenever you do you just do table report of something. So this has a lot of very useful features, and since this is an HTML file, you can just generate the table report, you export it in HTML, and you can share it directly with someone else, which is very convenient. Another thing that you're likely to need to do is to do the cleaning of your data, and this means usually a lot of boring things, like you need to convert data types, you need to find what are the null values, you need to find formatting stuff. You would like also maybe to have a consistent numerical representation of your data. Sometimes you might have columns that are completely useless, like you have a column that is completely constant or a column that has way too many null values. The cleaner can just remove all of that for you. So basically, the cleaner, and then you can select, you can pass some, like this. You can say, okay, I want to drop all the columns if they are constant, and maybe I want to pass a specific datetime format so that I have a not standard datetime, and I can just pass it directly from there. And in my personal experience, this is very convenient, especially because whenever you're starting with a data frame, you're probably going to do the kind of things that the cleaner does for you. So whenever I start a pipeline with the data ops, I always start with the cleaner. Speaking of time series, another very useful feature of Skrub is the datetime encoder, and it does exactly what the name suggests. So it will take a time series column, and it will pretty much explode or transform all the parts of the time series into specific columns. So if you're going to have a column for the year, a column for the month, for the day, which you can of course you can do with pandas, but this is just the datetime encoder is going to do it for you. Additionally, and we will use a bit of this in the tutorial, there are some additional features that you can add, like the number of seconds from epoch, the day in the year, and if you want, you can also add periodic features like the circular encoding, or like know it as trigonometric encoding, or spline encoding. So this is what periodic features look like. You can see that you can encode hours in a day with a periodic feature, the weekday. We're not going to use this in tutorial, however. Another very important feature of Skrub is the table vectorizer, which is pretty much taking a data frame and it's doing all the feature engineering for you. What the table vectorizer does is decides, depending on the type of the columns, what to do. So if it is a number, it will at the moment default do nothing. But there is a transformer that helps encoding numerical features for neural networks. However, if you have a datetime, it will apply the data encoder. And if you have a text or a string column, it will decide, depending on how many unique values you have in that column, whether it will use a low cardinality encoder or a high cardinality encoder. I'm not going to go into detail on the high cardinality encoders, but you can find everything in the documentation. One of the things that Skrub provides is a wrapper for a language model encoder, so you can get a language model from Hugging Face and just pass a column to that language model, and it will give you the embedding for that. So if you are working with text, that is very convenient, but just know that it's going to take quite a long time, especially if you're not working with a GPU. I'm not going through this. This is just to show you how many lines of code you need to write to get a very simple scikit-learn pipeline where you just use reach. Because you need to make a pipeline, you need to select columns, you need to start to scale, or you can just use the Skrub tabular pipeline and you pass reach, and it will do everything that I've just shown you for you. It will also select the best parameters for the table vectorizer. It will encode the feature engineering with the table vectorizer. And basically, you're getting a very strong baseline that runs with whatever model you want to work with. By default, if you just pass tabular pipeline of classification, it will use the scikit-learn histogram gradient boosting classifier. Otherwise, you can just pass a reasonable model and it will do everything for you. Now we have a pipeline. So we gather some data, the data set, we explore the data with the table report, we pre-process the data with the table vectorizer or the cleaner, we do feature engineering with one of the various encoders that Skrub provides, we build a scikit-learn pipeline, and then we profit for it. So, what if we had a better pipeline? This is the questions that we had when we were developing the Skrub DataOps, because there is a realistic scenario that is actually not covered if you're only working with scikit-learn API. So that you're a data scientist, you need to train a machine learning model, but your features are not in one single table, they are spread across multiple tables. There are a number of issues with this, because as I was saying, scikit-learn pipelines assume that everything that you have is in a single feature matrix X. However, you might have different things, different features coming from different tables, and you want to combine them properly. You cannot, any kind of operation that you're doing on data frames cannot be tuned. So you cannot say, okay, I need to group by a specific feature and I want to aggregate in some way. Do I aggregate by sum? Do I find the average? Do I find the median? You cannot use grid search from scikit-learn just for this. You need to keep in mind that there is data leakage. So if you are trying to do training and validation, you need to make sure that the lines that you're using are actually, you're not passing the test set to the training, in the training of your pipeline. And once you've finally handled all of this, you have all your code, you've gotten everything ready, you want to share this, and normally you would have already some kind of Jupyter notebook or a scikit-learn or like full script, but you want to make sure that everything that you've done, including a hyperparameter optimization, is actually tracked. And this is not simple. So the DataOps are trying to actually address all of this, because when another one pipe, they come to the rescue. So the idea of the DataOps is that they extend the scikit-learn machinery to multi-table operations. They track all the operations that you do with a computational graph. They can tune any operation in a computational graph, which I am going to call the DataOps plan. And they can be persisted and shared easily by generating a learner, which is a single binary file that you can just pickle and then you load it again. You can provide new data and it will run all the same operations that you've done on the new data, including getting a prediction if needed. So, just for terminology, so you are prepared for the tutorial. A data op, singular data op, is wrapping a single operation, and it can be combined and concatenated with other data ops. A sequence or a combination of data ops is a data ops plan, and the data ops plan can be exported as a single standalone object, which is called learner. And the learner is what you would have a scikit-learn estimator, but the scikit-learn estimator takes just x and y. The learner takes a full dictionary of values, because you might need to pass all the tables that you are using to combine to run all the operations. The data ops, as I was saying, they're wrapping around user operations, where the user operations are anything that a user might need to do. So a data frame operation, like a merge, buy, aggregate, everything, querying, selecting, anything that you want. And in scikit-learn estimator, so you want to apply a random forest, a ridge, you want to apply some kind of scikit-learn transformer, or any kind of custom user code. So say that you have a custom code that needs to convert your proprietary data into some kind of actual pandas data frame. You can also embed this into a data op. You can fetch your URL. So everything that you're going to do is just, you will be passing to your learner whatever the path of the thing that you need to load, and the learner is going to do everything for you. So basically, the ops record user operations so that they can then replay them in the same order and with the same arguments on unseen data. How do we start with the data ops? We need to declare some variables. And the variables are just going to be declared as Skrub.var, and they're going to have a name. And then additionally, you can pass a value. This is not necessary. The advantage of this is that data ops are all deferred operations. What I mean by this is that they are not eager, so they are not actually evaluated until you tell them to do that, either by running cross-validation or by asking the actual code to evaluate. So the advantage of passing a value here is that this will be used as a preview, meaning that at each step of your development with the data ops, this preview will be computed with the latest operation. And this is very useful for spotting mistakes, because it will try to evaluate on the data that you have passed, and it will detect, for example, if you're trying to apply a list, a pandas data frame operation onto a list. And it tells you, the list does not have the index, no, sorry, that's a bad example. The list does not have a group by operation, so there is some mistake here. So this is the advantage of having a preview. Market X and market Y are how the data ops are dealing with the leakage problem. The idea is that if you pass a variable and say, okay, mark this as Y or as X, then whenever there is a validation with cross-validation, then the Skrub data ops are going to only use the training samples for the training, and all the operations that are going to be done after starting from your X are always going to be aware of which lines need to be used as training and which ones are going to be used as test. So yeah, basically the variables are the inputs to the pipeline or the data ops plan, and Skrub is splitting X and Y for you when there's training. This is just an example of how you would build a full data plan, but we will show this better in the tutorial. First we define an estimator. This is a variable, as I was saying, and we can apply an estimator, which in this case is the vectorizer, to obtain the vectorized product, and then we can apply a pandas operation, which is a group by, on the vectorized products, and we get the aggregation of that. Then we can combine this with the starting feature matrix, and we can apply a predictor in order to get our predictions. And I'm not going to go into detail because this is what the tutorial is for. As I was saying, you can export everything as a learner, and this is very simple. You just get make learner. Or if you have done some kind of random search or aggregate search, you can just get the best learner from that search, so it's going to save the best hyperparameter set that they found for the search. Then you pick on this, and you load it and apply it. As you can see, this is a dictionary rather than X and Y. The other important feature is that of the hyperparameter tuning. As I was saying, you can actually tune everything in a data plan. And this is done using the choose functions provided by Skrub. So what you can say is you can choose from a given list of options, an integer, a float within a range, or a Boolean variable. Or you can just say, okay, I'm not sure if this specific set of operations is useful. I'm just going to put this as optional. So whenever you're doing another search, you can say, I don't know if joining this table with this other table is actually bringing useful information. I'm going to put this as an optional and find out when I'm doing the hyperparameter search whether this operation is useful or not. You can nest everything. So here I am saying, okay, I don't know which one is the best dimensionality reduction method. Let's just use both PCA and select the best. And I don't know which is the correct number of components, so I can just nest all of these. I just nest the choose integer for the number of components in both. And this is actually simplifying a lot, especially if you have a complex grid of hyperparameters, because you just put everything where you're defining the object, and the data ops are going to handle that for you. You can then observe the impact of the hyperparameters using the plot, parallel coordinate plot, which basically is going to show you, this is not animated, but we're going to show you the tutorial, the animated version of this. You can actually select, this is actually done with the plotly parallel coordinate plot. Yeah, this is done with plotly, but there is this is actually interactive. You can select, you will be able to select which ones are the best scoring configurations to see actually what are the hyperparameters that you want to check. This is almost the end for the introductory talk. So this is just like links that you can kind of follow with us. And now we're going to start with a tutorial. It's going to first be so there will be first a small part about the getting the data. Then it will be feature engineering on the data, and then finally actual prediction with it.
Do you have any questions?
Any questions?
Yeah, I found very interesting what you said that you can parameterize the inclusion or not of an Excel table. But I would worry, I don't know if you have explored this, but I would worry that, of course, when you're doing the fit in the beginning, maybe it's a very rough fit, and then maybe all those columns are not useful to you. And then you maybe dismiss the whole table, and maybe individually, if you had those columns, you maybe would recover one of them or two of them for the final fit. But I don't know, like the path to get there, if the fact that you maybe dismiss the whole table, how that will affect the fit of the final, like maybe it would make it harder to get into reuse it.
Yeah, so for that, it was a thorough example of you can just drop the full table, but in the tutorial there is a better example of what you're saying. So what we are doing in the tutorial is going to be, let's add all the features that were generated, and we try to drop some of them as like the dropping is itself a hyperparameter. So you can actually check exactly what you're saying, that some of the features might be useful, but we don't know which ones. So the idea of you can drop the full table is more like you can do like you can remove a full branch of the graph. It's a possibility. I'm not saying that is the correct way to do this.
Okay. So it's big enough. So just to remind where the stuff are. So if you go on the schedule, you will get the static website where you have some notebook, but then you will get as well the Git repository, which is these things here. And you have Jupyter Lite if you don't want to have any instance. So everything should be compatible. I mean, it was running at least yesterday. And otherwise, as it was mentioned before, you have an environment.yaml for Uconda, a requirements.txt if you want to use UV or pip, and you have Pixie file if you use Pixie. And the instructions here are written for Pixie because that's pretty handy. And that's it. So what it will look like, we'll look at this. And the first thing that I will go here, so since that Jupyter Book is a dependency, you can always, if you have the Python file, you can right-click, open with, and a notebook, and then the Python file will be like scrapped as a notebook as well. And I didn't open the right one. So the first one I want to check is the fetch weather. So right-click, open with, notebook. So the idea here is a couple of weeks ago we did a tutorial on forecasting with Olivier, which is here, and we wanted to use Skrub and to see if we wanted to do all the data pre-processing by hand, how this feature will be useful. So there's already libraries that do forecasting, and they are pretty good, and they can maybe do whatever we do here in a simpler manner because it's integrated within the models to do like the like feature and stuff like that. But what we wanted to do is build everything by hand and to see if something that is not built for scikit-learn, because now we have this flexibility of preparing the data and declaring X and Y whenever we want, can we use the scikit-learn models to do that without like touching the API, let's say. So how much flexibility we have. So that's a bit like the idea behind these tutorials. So here we have only 1 hour and a half, so we do 2 notebooks. I will put later on a link to the full forecasting where there's more machine learning implied, but if you want to go further, then you can always go inside there. And right now what I will explain is what do we try to predict, which data we are fetching, and then so Ricardo will go on the feature engineering, and then I will take back the notebook on like the forecasting when we want to forecast at one horizon. We'll focus a bit more on Skrub rather than on the forecasting issues, just because like that's a Skrub tutorials. But I'm happy as well to speak about the forecasting, let's say the use case if you want to. Okay, so the idea of the tutorial is to forecast electricity load in France. And the idea here is that we can like collect the data quite easily, but then as well to predict, to simulate that we say that we have like 2 sources of data and we want to merge together some data. So one good source of data would be the weather forecast. So if I have weather forecast, I can then forecast the electricity load. So this first notebook is something that you don't need really to execute, but it's just to show you how, because we already have the data locally, okay, we grab the data to avoid that you have to all go and pick up some data from the API of OpenMeteo, but it's to tell you what are inside those data. So for the weather data, so you would have the code that allows to basically replay the fetching, but the idea was to say, let's so I will just execute the cells here and to show France. Let's pick up some country in France that are like the largest cities in France, because they might drive like the electricity load. And in addition of like the largest cities as well, then we picked up some of the city that's to map basically that we have a uniform peak. So for instance, here there is Limoges, which is a very small city in the middle of, no, it's not that small, but I mean it's not very big. But the idea was taking a point here in the middle of France to have like a kind of a grid, and we're just missing something here. I'm from there, so I'm very not happy with Olivier. But otherwise we try to get like some extreme points in all France, and so how the thing was done here is that we ask an LLM so we pick up the cities, we ask the coordinates, and then we just used IPy widget and the map basically to just map those things into the map to be sure that the LLM didn't do any mistakes. So somehow it was kind of working. And then here you have basically the call to the API if you want to recover the data. So we use open meteor request. We send the API for the different cities. We recover, like you have many features that you can add. So we just like get a couple of them. So the temperature, the precipitation, the winds, cloud cover, soil, moisture, etc. So there is some that we know that will be informative. So most probably like the temperature and the precipitation can have an impact. Some that we are not really sure, like soil moisture. But actually this is pretty good for our tutorial because those we will see later have been collected only from a certain point, so there is missing data, so how do we handle those and those type of things. And the idea is to collect everything, build a data frame, which is what we are building at the end here, and return the data frame and then store those into Parquet file. So if you look at here, back in the content, you have a data set, and here you have a bunch of Parquet file where you have the weather underscore, the name of the city, and then this is all the data that have been collected from this API. Okay, so that's more or less what would this file doing. And here we already cached basically the data, so everything is already cached. And the important part here is really to understand that the data that are inside are forecast. So they are not the real, like what we measure at the instant, is what was predicted by forecasting models for the weather. Okay, so that's really like we're in the real setting of if today I want to have like the forecast of a model that tell me that tomorrow it will be that weather, and then by using this information, then I can predict as well what will be the load in electricity. Okay, so that's for more or less the first notebooks, and now we can directly go to the like real things, which is the feature engineering with Skrub.
Okay, so yeah, so the idea for this part is we use Skrub and Polars for trying to doing the feature engineering all of this, and we'll be going through this and trying to explain also the Skrub part of it, of course. And there will be a small example. Why is it not from the side? Is it not done? Because
Shift enter. Do you want your computer?
No, now it's working. Well, okay. I was in the wrong side. Anyways, so here I'm just importing the usual stuff. And the first thing we're going to do is to generate two Skrub variables, which are the historical start time and the end time, just to show that Skrub variable can be any kind of object. In this case, it is a single date time, because we want to generate the time range between these two extremes. And we do this with a function which has been decorated, very important, with the Skrub deferred decorator. And this is important for a number of reasons. As I was saying before, data ops are not executed eagerly. So you need to wait until you get to the point where you're calling eval, or you're training, you're applying some kind of transformer before the entire evaluation is done. This means that if you're trying to apply an eager operation on a data op, it will usually complain. It will tell you, this is going to be evaluated later. I do not know what is the actual value of this. I don't know what to do with this, and it will raise an exception. What you do is you do your operations inside a function, and you decorate this as deferred, and this is basically telling Skrub, okay, everything that is inside this function is as it is. So in this case it will be, okay, this is not a Skrub variable, this is just the content of the Skrub variable. You write your entire code inside this function, and the result of this at the end will be a data op. This is a number of advantages. One advantage is that anything that you do in a different function is just going to be inside a single node in the computational graph. While if you try to write the entire code eagerly, you're just going to add all the operations that you've done, which makes the graph unreadable. And I like that, to me, this is easier to understand in a way that whenever you're inside a deferred function, you can forget anything about the types. You're just going to write your own code as you would with if you're working with polars, you would just write your own polars code. The only thing is that the return value of this is not going to be a polars data frame in this case, it's just going to be a data op that contains the result of that. So what is happening here is we are building the time data frame, which is just a time series, which is an actual data op. And what you can do here, if you have GraphViz, and I don't remember the other dependency installed, you can click on Show Graph, and you will see all the operations that have been done up to this point. So we have declared two variables, historical start time and end time, and then we have called the function build historical time range.
So maybe here, the first time that you execute it, it might ask you to run, you will not see the graph and it will tell you like a sort of warning, and it's because you need to write -c inside the terminals, and that will initialize basically, I don't know if it's GraphViz or PodGraph or something like this, and then it will work if you restart. Okay, so if you see like the warning, I mean that's the reason.
Yeah. The other thing that you can see is that there is a table report that I've shown you before, and what is going to show you is the preview, is the content of the variable, in this case, time. So rather, it is showing you the preview of the result, the final node in the computation, in this case is the time series. And this is very useful as you are developing, because you see how your data changes over time with all the operations that you're doing. Let me continue on. And here, what I'm doing is I'm declaring a variable with the data folder. So I'm saying pass whatever you want, you pass the data folder, and here we are evaluating this variable. So I've been kind of shooting this word, evaluate. The idea is that you need to actually transform, in this case, the variable from a data ops to an actual path. And this is what the evaluation is doing. It's just running all the operations that we have done and getting you the final result. In this case, the final result is simply the value of the variable. So we can reuse the data source folder, which is a variable, and okay, it is scrolling more than I want. So we have another variable here, which is a list of city names. And there is another deferred function where we are going to read all the files from the data source folder. We are going to take the name of the city, and we are going to create a new data frame or a new data ops variable that contains the time, and then for each city in the list of cities. Here, I hate how it's scrolling for itself. And it will just contain all the temperature, precipitation, all the other features we've done in the previous notebook. For every city, you can see it at the end, the name of the city. So in this case, Paris, precipitation in Paris, wind speed, and so on. And this is a lot of columns, there's 61 columns, and all of these are for all the various cities that we have. So this is just going to prepare the weather forecast features for the cities. So this is one of, as I had requested before, this is one of the tables that is going to be put together with the others. The other feature that we would like to use is the calendar, because as you can imagine, when it's Christmas, for example, the electricity load is going to change a lot. When it's a holiday, when it's a weekend, the electricity load is going to change a lot because people who do not work are not moving and so on. So this is going to be the first exercise for this, and it will be using the Skrub data encoder. I introduced it before. And the idea is to create, adding the calendar, some of the calendar features using the data encoder. And the idea is that first we need to create the data encoder, like this. Then we need to rename a column to calendar, because then it will be used later, and we want to keep the time column as it is. This is going to be a new data frame that we're going to merge. And we want to apply the data encoder to the data frame, and finally we're going to store this inside the time encoded data, which is just going to be time encoded equal to the transformation we want to do. And this is going to take the encoded features that we want. And this can be done very rapidly. I'm going to give you a couple of minutes to do this.
Yeah, 10 minutes. Between 5 and 10. And then if you have any other questions or like we can as well pass around if you need some help as well for the setup at the same time. Yeah.
In this case, the data fetching. In this case, as I understand it, data fetching is outside of Skrub. Is that correct?
Yeah.
Yes.
Yeah.
Would it be relevant also to actually have a data op that does the data fetching? So you just specify cities, for example, or and then
you can create the data fetcher and put inside the variables. Here is just that we didn't want it that everybody just go and has the API, and that's because we will have limits and etc. But otherwise, you could replace like the dataset by just a function that make queries somewhere, and then you can replace the query. The problem is that, that could be useful. I mean, it needs to be done with a nice caching mechanism. So like this, you call it or you load from the cache if you have it, otherwise you just fetch from the data. But the nice part is that afterwards, at the prediction times, it's the same API, so you can just replay on a new data set, and then that will work. So the idea is that, you can do exactly that. Yeah.
It seems the online versions are not working, so it's.
I will look at it.
So it's let's get it for both.
It's a reference link. And it actually
okay. So
you need to remove the GitHub.
So this one. Okay, so if you go on the website, so probably is that, I messed up the link. If you click on this one, I'm sure it works.
okay. Yeah.
Okay, so go on the website and then the repeater in that case. Sorry about that, wrong link.
Okay. Okay, so you can move on. So the solution, as you can see, it's also in the notebook. We first need to define a data encoder, pass out the weekday equals true to add what day of the week it is, what is the day of the year, and we are going to turn off the total seconds. So this is a data encoder object from Skrub. And what is going to happen is first we're going to rename the column time to cal in the time data frame from before, and then we apply the data encoder just as a scikit-learn transformer, and the result is going to be the time encoded data hop. We can show again what are the operations to be done here. So call the method rename, apply data encoder, and the result is close this. Is the new data frame that has the new column names and then the all the path of the day. So the year, month, day, hour, and week. It's important, like part of the reason why we have to rename here is because by default, whenever you pass a column to a Skrub encoder, it will reuse the column name from before. So we would have a new data frame that has time underscore year instead of cal, which is not, in this case, it would not be very useful. There is another exercise here, and the idea for this is we take, so this is a defer function, and the idea is we're going to write inside a defer function the code for extracting the country holidays using the holidays package. And what has to be done here is to find what is the minimum column, the minimum year, the maximum year, so the final year, and then check using the holidays package whether a date in a holiday is a French holiday. So we also need to specify the French locale. And then you will need to apply the function, so the deferred function you're going to write, to the time data. And the result should be called isFrenchHoliday. So you're going to have the function that is going to do something to the data, and then the new variable should be called isFrenchHoliday. And then we want to concatenate the time encoded from before, the isFrenchHolidays from now, using the Skrub.skb concat. And for the .skb concat, you can go and check the documentation. And for holidays, you might need to check the documentation for the holidays package. And I will leave you a few more minutes and then continue with the solution. Okay, let's move on also in the interest of time. So this is the function that you might have written or something similar to it. And the idea is we take the time data frame from before inside a deferred function. We convert the time zone to Paris, France. We find what is the minimum year, the first year, and the final year of the holidays, and we ask the holidays package, the country holidays for France, and the years in the range from the minimum to the final year. Then we select the time, the date, whether, so we are going to add a new column that is basically telling us whether the current date is a holiday according to the French holiday calendar. And the result is going to be a final calendar data frame that adds all of the features, including the calendar is holiday. So this is the calendar table that will be used as additional features for the training of the data.
Can you show the stats?
Oh yes.
For the calendar.
Oh yeah.
To check that it's not all zero.
Yes, and it's a boolean. But the problem is that in the expressions you're not showing the distribution. So
here it's two unique values.
yes.
It was. Not.
Yes.
My laptop
Your screen is unplugged.
What? Oh, all right.
You can unplug.
Yes.
It was two unique values and 10, 1%. No, 0.1%
Zero.
were holidays.
Okay.
Yeah. Yes, so you can also see, yes, the calendar day of the year. We could show this with, and then with a table report. So yeah, here you see the distributions, and you see that the calendar is holiday. There are 3.1% values that are not zero. Those are the holidays. And yeah, it is just showing also that it is processing the table report. For convenience, you don't want to actually have the full generation of all the graphs whenever you're running the dog, which is why we remove those from the by default. You can actually change that, but by default you're not going to have it.
And can you explain the association tab that you get?
Oh yeah. The association tab is showing you which one is the column, which columns are strongly associated with each other. So if I'm going to do something, if you have numerical columns, you're going to have Pearson correlation. If you have, and then there is a Cramer's V that is basically telling you for categorical features, for any feature, it's just going to bin the values in the features and it's going to compute the association between that. This is maybe not the best example because we have only numerical features for calendar years, but it is a useful indication if you have redundant columns that have a very high association. You might want to look at those and possibly drop them. Yeah, this was a part of the tutorial which was kind of changed over time. The next part, the final step, is going to add lagged features using the load data. And this is going to be just a default function, and hope I can explain it properly. So the idea is that first we need to load the actual load, and you will be able to see this, and you can open it, for example, here, and you will have, this is what it looks like, and what we're actually interested in is only the total load. So it is dropping, we're going to drop the load forecast, and then this is going to parse the data, basically this column parsing the date time using the specific format, and then we just get the electricity row where did I go? Here. Which is just going to, oh sorry, I skipped one step. So this is actually going to show you the electricity, and the problem is that there are a few null values. So we want to look at those null values, because this is the fourth column that we want to use as a target. So we want to make sure that there are no null values in target. And in this case, we're going to interpolate using linear interpolation. So this is what it looks like right now, at least in one of the intervals where there are null values. You see there is a hole here, and we can interpolate it just to have a line, so we have values for all of those missing points. We want them to add like features, which is basically telling us what is the predicted, what is the next in the future. Is it in the future? No, it's the yeah.
You were like, so basically you want to use past data to predict the next one.
Yeah.
So that's why you want the forecast, the electricity load from 1 hour to some hours before, because it can allow you to predict the next one.
Yeah.
These are Rolex statistics, right?
Yeah, that's a running window. So that's what we call like fixture.
For me, like for midnight, you want to check what was the load 1 hour before, 3 hours before, 5 hours up to 24 hours before, and then there are also some running statistics. We're saying, okay, from midnight, I want to see the average for the past 24 hours, and as well as the median, and the interquartile range, which is telling me what is the variability over the past 24 hours, if it was very variable or if it were, and the same for the 7 days past. And these are particularly easy to do with polars compared to pandas, which is very nice. And it's one of the features I really like about polars. So basically, we are just shifting by a certain amount. In this case, it's like 1, 2, 3, and 1, 2, and 3 hours. 24 hours, 1 full week, and then we're doing daily medians. And we can plot this in here, and you can see that this value is you can see the key is load megawatt, which is the true value, and here this is the load. Why is it not selecting it? Shifted by 1 hour, 2 hours, 3 hours, and these ones are the interquartile, I think.
Yeah, for the median.
Ah, yes, the rolling median for 24 hours. So you can see all the various features. So now we have the final data set, because we have the all the various features we want to generate. So we start with the prediction start time. And what we want to do is to find, in this case, it's just to prepare the original version. This will be preparing all the horizons from 1 hour in the future to 24 hours in the future. For this specific tutorial, it's just going to be, let's try to predict 24 hours in the future. So this is just going to the code to prepare the features, the prediction target 24 hours in the future. And one thing that I want to point out here is this function, subsample. So what you can do, and this can also be done very early when you are doing the subsampling, is kind of depends on the task that you have, but it is that we have been working with the preview up on all this time. The problem with the preview is that if you have a very large data frame as a preview, it's going to take a very long time to do each step, because the datatypes are going to compute everything on the full dataset. You can say, okay, I want to just work on a subsample, and say I want to only look at the first 1,000 lines of my data frame for the preview. This is going to save you time, because all the operations from now on, you're still getting the debugging advantage of using a preview, so showing you what is the correct, if you can do a certain operation or not. But at the same time, you do not do it on the full data, which saves time. And when you're actually training the data, this is disabled by default, so there is no risk that you forget to actually train on the entire data, and you can run the code on the actual full data set. The final thing is kind of renaming. Oh, sorry. Yes, we are kind of renaming the features so that we can then drop specific columns whenever we want. So we have the light features that we start with load, the weather features start with weather, the calendar features that start with cal, if you remember. And finally, we build the targets, which is, so we have the actual load, and so the train load and the target we want to predict. And this is almost done for this. We save this, all of this, for the notebook. You could actually continue from here if you wanted. This is also in topical, and it can continue. We can continue with the next notebook. So this was basically a feature engineering, all the things that you can do with Skrub using for feature engineering. Now it's going to be the hyperparameter optimization and prediction.
Yeah. Do you have any questions? No. Okay. So now we'll switch to content and the single horizon predictions. So the idea here is that we build all our data, and now we want to have a predictive models. So at that point, we have whatever we can use as X as the features. We have the target that we want to predict as well inside that data frame. So I would like to mark my X and Y, and I would like to declare, to add basically my data plan, a scikit-learn predictor, which is a regressor that will take those as input and be trained, be optimized, and so on. So let's start with the boilerplate imports that make everything works as well in Jupyter Lite. And we reload basically the data from the picker. And first thing that we'll do now is, because we are doing a single horizon, so we mentioned that the targets for our cases will be the columns that is named load MW, so megawatts horizon 24 hours. Okay, so we try for at time t, we try to predict 24 hours later. Okay, so that will be the value that we are trying to predict there. For later on, we start to create a name that we will use later. Basically, that will be when we do the predictions, and if we have a data frame, we want to name that columns, predicted underscore, just to prepend the names to distinguish the real target from the predicted name. Okay. So for the target here, if we want just to build it, what we do is that we take from all the target that were all the horizon, and we pick up only a single one, which is the one that we said at 24 hours, and we finally mark it as y. Okay, so that will be the variable that we want to predict. On the other side, now we want as well to do a bit of feature, let's say hyperparameter tunings. So we want to show two types of hyperparameter tuning. So one of them that Ricardo showed already in the slide is, and that's what I used to, is you have the machine learning models, and then you want to tune the hyperparameter of the model. But the first thing that we'll start with is that here, and it was the other part, we have many columns, and maybe we want to see the impact of selecting one column or dropping some of the columns as well on the prediction quality. So here we will take the full feature matrix that we added in, and we'll use Skrub transformer, and the job of that transformer will be to drop some columns. Okay. By default, we could say that we have this none, and it means that here we ignore so we just take all the columns that we have. Okay, so that would be the first options, and then we add some other options that during basically a grid search or randomized search, that we can pick up any of those cases. And what we have here is that, so if I get the load options, then I will just remove all the liked feature. Okay. If I do the rolling load, then that's the mean of those. If I take like the weather, I will drop the weather feature, the temperature, etc., etc. And at the end, we have one that is a bit specific, saying like, I want to drop all the data that are not Paris, just to see if actually having like data from all over France have an impact, compared just to have a single point in Paris, and that will be predictable for the full France. So here, that's one operation that when I will do like hyperparameter search, and that if I do randomized search, I will pick up one of those, okay? And then I will apply basically my machine learning model. So I will apply basically a regressor, where I do as well some hyperparameter search. So here, when I declare my histogram gradient boosting, I want to say my loss can be, I will vary the different type of loss, which to see if it has an impact, but like the default one is a square error. Otherwise, I have Poisson or gamma, which are as well proper square rules. We'll see that this doesn't have any effect. But otherwise, other thing that's much more important is like the learning rate of the models. Because if the learning rate is too high, then it's avoiding that my model, it will make that my model can overfit or underfit basically, depending on that parameter, so I want to tune it. And usually the interaction between these parameters and as well the complexity basically of each of the trees, which is like the number of leaves inside the tree. Okay, so we try, here we just like provide those, and then as well when doing a randomized search, it will pick up between those parameters and try different models, and then we can pick up the best one. Okay. And yeah, and I will just comment this just to show like the prediction here. So here, the view that we have is to apply this finally this very difficult graph. Okay, so this is what we did from the beginning. So we have all the feature engineering that are on the top. Here, the build feature was the one that was stating that's why this is my x. The y here is in orange is what I tried to predict. And here we have like this drop that we added just before, and then our histogram gradient boosting. And here's a preview. What the preview do is it does the, let's say, the fitting and predictions or already on the small samples, just to be sure to tell us that it works. So what we obtain here is just, let's say, a debug mode to tell us if it works. You cannot trust any of those values, but it's a debug mode to tell you, yeah, I'm able to predict with my models, okay? But it has been done fitting and predicting on the same 1,000 rows.
And only on the default values.
And only picking up, yeah, it doesn't do the randomize any search here. It picks up basically the default of the choose from, or the default of the choose float, or choose int. So for instance, here for the choose int, we define what should be the default, and for the choose float.
It's the half point between the two extremes. In this case, it's also log. So it's the logarithmic half point between 3 and 3.
Okay, so here a bit about Skrub in terms of things that you mentioned before. So this data plan, so like all the different variables, we have two interesting information. So one which is like the get data, that if we look at like the variable of get data that we have here, they correspond to, inside the graph, to the original variable. So they give you this information like, is what I need for my final model to predict is what I need to provide later on. Okay? And the second thing is what we call, so then a learner. So a learner will look like something like this. So it's kind of looking like a scikit-learn things, but the difference is that at predict time it will take a dictionary and not only X and Y. Okay, it will take basically a dictionary where all the keys will be the name of the data, and then we can add the values. And one of these things here is that it has these describes params, which will give you the informations of the value of that. Of the hyperparameter at that time. So here what we get is the default hyperparameters because we didn't make any grid subs there.
Also, the make learner is not
The
the make learner here is not like the learner you get here is not fitted.
Yeah, this one is not fitted. So here you have an option to say, do you want to fit it or not? But here we didn't run any experiment. And finally, you can 1, 2, 1, 2. And how do you do? Okay. Okay. And finally, what you can get, you can export basically from your final plan. You can export a full report in HTML that looks like this. So it's exporting graph. And when that you click basically on the graph here, on the side, you will have the information about where. So here we're inside a notebook, but basically if you are inside a Python file, we'll record basically the line that generating that nodes. Okay, so you can already track basically information where it comes from. And then you get the preview as well as what we had inside the notebook. So it's a location where we can have like all the different informations. And then here you can basically go in the graph above or under because to just like see the path of the operations and how they are linked. So this is like an additional like feature that can come together with the computation graph. Okay, so here what we did was to build like the full data plans. So now we want to evaluate it. To make a proper evaluation, we need to do cross-validations, and we have time series, so we want to combine with element of cyclone that allow to do that, and one of them is like the time series splits. So it's allowing to make sure that you are not using future data, basically to predict from data from the past. So it's doing like a kind of careful, but ensuring that you don't have future data. And an additional thing is that you can add a bit of times of data that you don't want to use between your training and your testing, such that, because otherwise it's very easy to predict the next data point if you have the past one. So you want to add a bit of gap here that you can burn and not use them to ensure that you have not like a type of leakage there. So in this case, what we try is to define a maximum trend size of 2 years worth of data. And we want to have a test size of 24 weeks. And we want to be sure that we have a gap between the training and the testing of 1 week. And so you need to pass those, and we make 5 splits. So if you pass this inside the time series split, then you will get the following split. And if we place a split to check basically the time range and the type of data, so we see that the trend size for the first split is a bit smaller because we didn't have enough data to get the two years. But the 2 years was the max. Okay, so here we didn't get our 2 years, but then like there are always 2 years. So this is one thing, and then the testing. So the testing is constant, and then we can look at as well like if we look at the trend time range and the test time range, we will see that we don't have overlaps, let's say, of like future data getting in. Another information that will be interesting as well for the analysis will be that the first split here, it's overlapping with the start of the war in Ukraine, and then that will have an impact basically on that's a very difficult basically a very difficult split when we try to predict, and we'll see that if we look at the metric there, then it will be a much more difficult place where we have a drop of performance for those reasons there. Okay, so how do we make cross-validations? So here, to make the cross-validations, we can take our prediction there, and the first thing that we do is we do outside cross-validation. So here we are not yet interested about the hyperparameter tuning that will come afterwards. Okay, so the only thing that we have our models, and we just want to cross-validate given this time series split. So it's really looking at the very similar to scikit-learn. So we pass CV and we provide like the time series. We can provide a dictionary of the different metrics that we want to compute. So here we are interested about the percentage errors, the mean absolute percentage errors, and the R2 score. Okay. So the second one is the proper scoring rules, varying between 0 and 1. If you are 0, it means that you are predicting basically the mean targets. And if you are above, then you are better, maximum is 1. And the mean absolute percentage error will as well be between 0 and 1 and give you like a type of, like say, a percentage of what you do as an error. So we can run that. It should take a bit of time. And if we look at the result, then we can see that if we look at the R2 on the testing set, so we don't have that much variance on the 4 last splits, but we have like the first split, as I was saying, that is a bit more difficult. And this is the reason is back to where the data come from. And on the map, we are as well like pretty good, around like a bit less than 3% of errors basically on the different splits. So here it shows you that you can quickly run the cross-validations one that you have your data plan. So just we wrote a bit of code to collect basically the prediction of one specific split. So here, which is the first fold. And by collecting what we have here is that we have the true predictions and the true values and the predictions. And then from there, we wanted just to make like a couple of plots to see in practice if we are really how our model is doing. And so in orange is our models, in blue this is the true target, and then we can see that we are pretty close, and that might be a bit difficult to judge anything regarding the quality. And and then like maybe we're a bit not super good at predicting basically like the very extreme low values or maybe the very high values like when you have peaks. Okay. So here I will go a bit faster because it's inside the analysis of the forecasting. But we can have several ways of one that we have all those predictions to go inside the forecasting, let's say, so I can check if my model, so the same way that we have word curve in classifications, we can look at the Lorentz curve in regressions. And in some way you want to be sure that you are succeeding to predict pretty good. And here what we have is like we have the oracle. So the oracle is in orange, and it means that this is the best thing that you can do. Okay, and then you can look at how close basically your model is. So here we are always really close between the oracle and the models, which means that we are able to predict. So these are another informations that are as well related to like the metric that we showed before. And then you could go more into details in, for instance, is my model well calibrated? So we can like run and do like reliability diagrams. So for instance, that's here we have the 5 models from the different fold. We see that they follow the diagonal, so it means that they are pretty much well calibrated. So they predict like in the order that they should do, and with the right magnitudes, with a bit of like. It's a bit worse basically on the extreme values. So it's what we could spot as well on the forecast. And then here is an additional analysis regarding, like, for instance, looking at the residuals. And so here there is not so much to see, but if we're interested about making the analysis, we can look at those and see if there is any pattern that we spot. Because if there is any patterns, it means that we need to go back to our models, because probably our model doesn't grasp like some specificity of our data, which link that the residual have a specific pattern. Okay, so maybe here there's something like when we do at the residual by hour and we go by hours, so maybe there's something around here, this area of like morning hours that something happened, but I mean more or less like it's still like pretty consistent. But let's pass on that and more on Skrub. So here, what we run is basically the external cross-validations. But we didn't do hyperparameter tuning while we put like some truths. So how do we do this tuning? So here, for gain of time, you could uncomment all the code here and you'll get basically the final things that are on the bottom, but I can at least explain the code. But it will take a bit more time because basically here we require to make 100 iterations of a randomized search. So you can do a grid search by getting basically the randomized search by calling make randomized search and pass basically the like some what you would put to a randomized search in section. Okay, so the type of CV that you want, the score that you want to optimize. So here, to pick up the best model, that will be the R2 score. How many iterations you want to do, and does it like fit the final model or not? Okay. So if you run this, and then you look at the results, basically you will get a table with all the possibilities that you tried, and it will give you a result. But the best one is to look at the parallel coordinate plots, where you can make basically the analysis. So if you look at the parallel coordinate plots, and here, so because you have plotly, you can basically select a subset. You can drag basically your understanding of which hyperparameter, what's the impact of the hyperparameters on the best models. So here on the set of best models, one thing that we can spot is that they always, I mean, a lot of them drop none. So it means that from the full set of features, basically it is always better to try to drop some of the features. I mean, in that case. Some other thing that you can probably check is like which of the features are predictable or not predictable. And like we see that we never drop, basically a good model never drop the weather or the temperatures, while some are just dropping things like the moisture and things that we're not sure that it was predictable. So here that's one thing that we can observe. Other thing is for the losses, we see that all the models use all the losses, so there is no real impact there. Regarding the max leaf node and the learning rate, this seems to be still to have a range of values which are good. Okay, so here for the learning rate, we have a bunch of values in the middle, which are most probably like the good range, so we should be lower than 1 and above 0.05 for sure. And these are an interactions with the number of leaves, and the number of leaves need to be large enough. So 3, 5, 8 is anyway too small. Okay, so we need to increase there for sure. Okay, so this part here did, let's say, the internal hyperparameter search. So how do we combine the hyperparameters, this internal search, and the outer that we did before, and that's the nested crossval. And the nested crossval is actually, again, commented here because that will take a lot of times, so you can run it. But, so let me just, no, I can. So let me explain what is there. So, in some way, you have this Skrub.crossvalidate where you can specify the learner and the environment. So here, you provide the randomized search that we just created before, which is this variable here. Okay, so we make the randomized search. So we have to pass it, and we have to as well pass the full data set. Okay, so retrieve the data, because now this learner doesn't have the data attached to it. And then the other part here is exactly what we use inside the other cross-validation when we try the outer loop alone. Okay? So here it means that you just need to provide like the randomized search and the full data sets, and it will do the two cross-validation. So the outer one to validate the models, and the inner one to find the best model with the best parameters. Okay, and afterwards, when that you run all of these, then you get like 5 folds, and for each of the folds you find the best model that's better with the best parameters. Okay, so it's what basically you get there, and then you could do more and look at basically explore which model, which parameters we selected, and so on. Okay, so we have 5 minutes, so I'm pretty sure that will be too small, but here the final exercise is to replay whatever we got here, but instead to use the histogram boosting, is to use the linear predicted models with some instruction on try these parameters or try to tune this one, and then repeat those 3 functions like cross-validations, randomized search, and the external cross-validate. And with another model just to get a bit used to it, and with another type of feature, of hyperparameters basically. And then see how good this linear model is compared to the other one. So that's the aim of the exercise. So I can let you, like, if you want to start, you can do in the last 5 minutes. Otherwise, we can also answer any questions during that time. Okay? Yeah.
Is the output of a plan or a single output, or can you have multiple outputs?
You mean the prediction? Is my model?
Yeah, so here we have X and Y coming in to the model part, and we get a single output, right? A single data frame or a single variable.
Yeah, it's because my target there is a single one. So you can get multi-outputs. It's just that you need to have the models which predict multiple outputs. Okay.
Is it a single variable with multiple columns, or can you have multiple variables?
Oh no.
The output, the output at the end of a plan is the result of the final data op in the plan.
Yeah.
So that means that depending on what the final data op is doing, it will give you a data frame or a prediction or whatever.
Yes, but always a single variable, a scale variable.
Yes.
So you're kind of always going, you can have multiple variables going in, but you're always kind of going towards one
so
in the DAG kind of.
Yeah, it's basically it depends what your last step is predicting. So it is outputting.
Okay.
So here is like we have a model, it predicts single columns or multiple columns, but that is single output. I mean like the data outputted from there is like a single one.
Yeah. And one similar. So here we have X and Y coming in, and understand that kind of like the machinery helps that nothing kind of leaks between them. Is very nice. Can you have another input, which is, for example, some like information about the samples, which should not be used in the X, but is useful for error analysis, for example?
So not right now, but we work as well on this in Scikit-learn. So Scikit-learn since last year have what we call metadata routing. So in some way, information that you don't want to use for the predictions, but that somehow have an impact on pre-processing. So for instance, I want to evaluate with those type of groups, and then the scoring should take into account that thing, for instance. So in Scikit-learn, since now 2 or 3 versions, we have metadata routing that can be enabled. We just need to make that Skrub forward and activate this metadata routing, and then you should be able to say this learner take those columns as metadata routing, and at the end of the day you could see it as the input, all the preprocessing do a huge data frame, and inside I have some data, I have some target, and I have some metadata routing, and the mark X, mark Y, or mark metadata that could be just tell you like how to consider which column how to consider, and then the routing inside is the mechanism in Scikit-learn that is allowing to pass which data to which things.
Yeah.
So it's not yet done, but there is like
a plan.
This is a plan.
Great.
Time's up.
Time's up. Okay. Yeah, it's even overtime. So if you have any other questions, please find us anywhere. We'll be happy to discuss that. And I will put the link about, like, for instance, you have multiple horizon predictions inside the other class. So that can be interesting. Okay, thank you.
To nie działa na razie?
Wiesz co? Września raz działa, raz nie.
No, wcześniej też już.
I put it now because of what I will forget.
Nie pokazywał, że się rozładował. To jest tak.
No właśnie załadowałem. Aha, tutaj was trochę.
No, tak jakby z tym przełącznikiem.
No, wezmę i dam.
Thank you. I thought that was very good. Quick.